Today we get to talk about mass spectrometry. Mass spectrometry, what we're going to be doing is we're going to be getting molecular weights on a very small amount of sample. Now these mass to charge ratios that we're talking about with the molecular weights is not only the masses of the molecules, but the fragments, and we get to learn about their relative abundance. Okay, and this reveals information about the structure. Doesn't involve electromagnetic radiation spectrum, so there's no absorption or emission. And when we ionize our molecule or molecules of interest, we're not looking at the anions, we are focusing on the cations when we do mass spectrometry. If you say, well, can you look at anions? The answer is yes. You'd have to reconfigure your mass spectrometer, and it has been done, but the most common technique you'll see for your mass and analyzer is to be focusing on your cations. That's what we will talk about today. All right, so we know what we can get for the masses. If you have a particular compound, if you have a mixture that you're testing, you can look for the molar mass of that and then look at the fragmentation pattern. So we'll talk about a technique like that. And if you look at your mass of the molecule or molecules in high precision, you can also determine what the actual molecular formula is if you know what your choices are and you know what the natural abundances of your isotopes are. Okay, so let's go into a little more detail here. Hang on one second. There's always a little bit of technical difficulty here. Okay. Okay, so when we talk about mass spectrometry, there are two aspects that I'm going to actually focus on. First is ionization of your sample, and second is the analyzer, so the mass spectrometry technique. I'm only going to give you a sampling. There are a number of ways that we use mass spectrometry. It has become such a powerful tool. All right, so what are the common ionization techniques? And typically, these techniques that I'm showing you are going to be for molar masses less than 1,000. Okay, the first one is electron impact. So we have a beam of high energy electrons and it hits our molecules as they're vaporized. And when it hits the molecules, it strips off actually an electron. So when you get the molecular ion, it's actually M plus with a radical. It's a radical cation, which then subsequently fragments. This is a hard ionization method, a high energy method, so you do get a lot of fragmentation. Sometimes you won't even see your molecular ion because it fragments too quickly. However, sensitivity is really good. You're looking at nanogram to picogram amounts. The advantage, if we use the same conditions for EI, we have a database that you can search across the fragments and you can search across actually your molar masses, and that allows us actually to figure out what's there, so you get a lot of structural information. Because gas chromatography is already in the gas phase, what's happened is that you can interface easily with gas chromatography, so you get a GCMS. Anytime that you get your peaks from your GC going through, you can get the molar mass of it and the fragmentation pattern. Okay, so that's really nice. We use it primarily for small organic compounds, and we can get structure determination information out of it. Okay, a softer technique. So what happens is that you don't get a lot of fragmentation. You get some, but not a lot because it's a softer technique. So when we ionize it, we do the lower energy, but still able to ionize it. What we actually do for chemical ionization is we have small solvent molecules like water, methanol, dichloromethane or chloromethane. And what we do is we ionize the solvent molecule. So then as we solvate Vaporize and solvate are our substance of interest. It is protonated not because I'm stripping the electron, but because it's combining with a charged solvent molecule. So under acidic conditions, that's how you get your molecular ion +1. If you have water, then protonated water, then that's how you get the N+18. You don't get very much fragmentation at all. It's nanogram to picogram amount, so it's sensitive again. And usually you see your molecular ion, you don't lose it. And the atmospheric pressure, chemical ionization, interfaces with liquid chromatography. So instead of, when we do HPLC, the high performance, liquid chromatography, the output we run through a mass spec, and we can get the molar masses of our compounds. Okay? So you get the molar mass determination. Alright, when we do techniques for large molecules, and we can actually use the previous techniques, but for larger molecules we tend to use these techniques for ionization. It can go up to 100 kilodaltons. There's really actually not an upper limit. There's electrospray. Okay, so basically what you do is you have your non-volatile compounds, you have it dissolved, and then when you volatilize it, you strip away the solvent, and what you're left with are your volatile compound, or your non-volatile compounds that are ionized. Now what's nice is you can form multiply charged ions. And what that means is if we're looking at mass to charge ratio, if I have multiple charges on it, then those ratios will still fall within the range of our mass analyzer. So we can actually look for very large molecules. Also, it interfaces with liquid chromatography extremely well. So in this case, if I'm doing peptide and protein work, I could run it through an HPLC, and then the output would go to electrospray and then to the mass spectrometer, okay, to analyze it. So we can look at peptides and proteins and complex mixtures. Okay, another technique for ionization is called laser desorption. So you have a matrix that you have your substance, your mixture in, and then you use a laser and it hits your matrix, and off of it bounces your ionized compounds, and you will have some matrix coming off as well. It is in the microgram to nanogram amounts for sensitivity, so a little less sensitive than electrospray. But you can also look at large molecules and mixtures. The other thing is that it's also been known to be used on cells. So as long as you have your cells, you're looking at tissue, you put it in the matrix and you use laser desorption, and it will bounce off. So you can analyze actually very complex mixtures like cells in order to find out their composition. Okay? Now, what about analyzers? Well, the classic one that we're going to be talking about and the results that we will be analyzing will come from this is called a magnetic sector mass spectrometer. Okay, so when we talk about mass spec in organic chemistry, we're talking about EI, the electron impact ionization technique, and a magnetic sector mass spectrometer. It's very high resolution, gives you exact masses. Okay, a quadrupole is low resolution, but it's high throughput. So it doesn't take up nearly as much space as a magnetic sector. And since it's high throughput, you can couple it with an HPLC. So now we can use HPLC, go to electrospray, and then run it through a quadrupole. Okay. There's also time of flight, and there's no upper limit, mass to charge limit on time of flight, and that's also high throughput. That too can be coupled with HPLC. And finally, we'll talk about tandem mass spec, in which you have two or more mass analyzers coupled together. Okay, so let's take a look at the magnetic sector mass spectrometer. Okay, so here we have our probe and our ion source. So our sample comes through. Our ion source, remember these are high speed electrons. They go through. They're shot through my sample that's in the gas phase, and then this forms your ions. Okay, my accelerator plate, what happens is I have your ion beam coming here and accelerates all your cations through. And what you do is you actually change your magnetic field strength. And as you change it, if the ions are too light, they'll bend too much and they'll hit the wall. If the ions are too heavy, they're not going to bend enough and they're going to hit the wall. So only those cations that match that magnetic field can follow your flight tube and make it through your detector slits and then into your detector. And so we count the number of ions there, and that's how you get your intensity. Okay? So as we go through and scan the various magnetic fields, that allows us to tune it so we can get our small, light ions, our heavier ions, and then the ones that are heavier even past that as we change our magnetic field. When we look at our resolution of mass spectrometry, we can get high resolution to 1 part in 20,000. What that means is if you know that you have a molecule with a mass of 44, these are all the possibilities so far. However, if you do your exact mass of 44.029, you can pick the correct one because this is 44.062. That's too far from your exact mass. So now you know it's got to be this formula. Okay, so that's how we can pick out the correct molecular formulas. Let's talk about our quadrupole mass spectrometer. Okay, the quadrupole, we have basically what it means. Quadrupole, 4 poles, magnetic poles. What we do is alternate the current. So as my ions go through there, you're basically going to follow your alternating current and not hit your quadrupoles. Once that happens, it makes it through this tunnel, comes on out and into your detector. Okay, so as you change your frequency, your voltages, you're going to get different resonant ions, and that's how you change your mass to charge ratio. Again, be aware, this is less precise, still has good resolution, but not as precise as a magnetic sector mass spectrometer. But what is nice about this is it's very nice and compact, and so we can actually link that up to our liquid chromatography instrumentation. Okay, time of flight. This doesn't really have an upper limit on our mass to charge ratio. Here I have a MALDI plate, so I have a solid matrix. I use a laser pulse, and what happens is it desorbs. That's desorption ionization. So the surface, some of those compounds will actually ionize, come off the surface, gets accelerated, and this is what we call a field-free drift region. So once I accelerate it, all of these should have the same kinetic energy. And if they have the same kinetic energy, then those lighter ions will fly faster through this flight tube than the heavier ions. So time of flight, we separate by the time of flight, and we see the detector, and that allows us to take a look at our mass to charge ratio and our intensities. Okay, tandem mass spectrometry. So here, let's just talk about doing mass spec with the magnetic sector. Okay, now, if I have a mix of compounds and I run it through my mass analyzer, but I use a soft ionization technique, then when it goes through the detector, I will see how many ions I have in abundance, very little to no fragmentation, so I can identify all my different compounds. If I do that same mixture and I'm in a tandem mass spectrometer, then I go through the mass analyzer, and instead of getting my ion abundance, I can tune it so the only one I'm allowing to go through after that is going to be of this mass to charge ratio. Once it goes through, I now use a different type of technique to fragment this compound. Goes through the second analyzer, and then when I look at the proportions, I have my molecular ion plus I have all the fragmentation. Now, why is that better than just doing a mass spec? If we have a pure substance for mass spec, right, and then we do EI, MS, then that makes a lot of sense. But a lot of times we're working with mixtures. And when we work with mixtures, then being able to separate it out by doing tandem mass spec, okay, is really important. Also, just so you know, for the soft ionization technique, if we're looking at liquid chromatography, we're going to be using APCI or electrospray. Those are soft ionization techniques, so we wouldn't get fragmentation like we would if we were doing a GCMS. Okay, so let's start interpretation of electron impact mass spectra. So we're using electron ionization, the electron impact, and the magnetic sector mass spectrometer. Okay, so again, high energy electron beam, okay, dislodges an electron, okay, forming a radical cation. So this is my molar mass. The mass to charge ratio would be equal to my molar mass. I can now, because that bond has just got a single electron in it, it can break easily. If it fragments, I can lose my hydrogen as a radical and have a primary cation. Or what can happen is that I'll form that and quickly have a rearrangement, lose a methyl radical, and get a methyl cation. So when we do the analysis on mass spec now for the fragmentations, one of the things that we want to keep in mind is what makes a stable carbocation. Okay, separation of ions, we talked about that for the magnetic sector and the deflection. Okay, so again, we're just repeating how we detect our mass to charge ratio and the intensity of our ions. So fragment it, flies through, okay, and we detect it. So let's take a look. So what's interesting about your mass spectrum is this. Because we have separation based on mass, you can detect ions as well. Okay? So basically, if this is my molecular ion, or isotopes as well, this is my molecular ion. The difference between this and this is 15, which means I lost a carbon and 3 hydrogens, a methyl radical, to form this one. So it's like you get cleavage here, it'll form a secondary carbocation. That's great. Okay? If I look at the difference between 100 and 57, what that means is I lost 43. Well, 43 is 3 carbons and 7 hydrogens. So if I lost 3 carbons here, right there, I lose this isopropyl group as a radical, then what I'm left with is a mass to charge ratio of carbocation of 57. And 43 here is basically if it splits and this became my radical and this was my carbocation. Okay, what about 41? Well, I lost 2 hydrogens as well. So it may be one of the things that you could be losing is an alkene. Okay, so not only are you going to be losing radicals and forming just a pure carbocation, but you can lose a neutral small molecule. And if you do that, you'll form a radical carbocation as well. So, can you assign every single peak? The answer is no. Sometimes you just get random rearrangements, and so some of them you won't be able to explain. But we're going to talk about the ones that we can recognize as a pattern for certain groups that are in your molecule, and others where, like we were talking about, the loss of your methyl, loss of your propyl group. Okay? Okay. So let's see some of these rules. So some of the rules to consider when you are predicting your prominent peaks in electron impact mass spec, the height of your molecular cation. Okay? So when you have a straight chain, it tends to be larger. If you have a lot of branching, it tends to be small. So let's go back, see how that's relatively small. If you compared it to just a straight chain, your molecular ion would tend to be larger. You're going to cleave at those carbons that favor a stable carbocation. If you have double bonds, cyclic structures, and aromatic rings, those stabilize your molecular ions. So you'll be more likely to see your molecular carbocation radical. And when you have double bonds, you're going to favor the allylic cleavage, because remember, the allylic group cation is more stable than a secondary carbocation because of resonance. If you have unsaturated rings, it can undergo a reverse Diels-Alder. So you have a cyclohexene, it can give you back, you'll get your ethylene, and you'll get your 1,3-butadiene. Okay? Aromatic compounds, when you lose substituents, you'll tend to lose it at the bond beta to the ring, and we'll go through that in a little bit more detail, so that you form your tropylium ion. Carbon-carbon bonds, okay, next to a heteroatom are often cleaved because you can stabilize those charges by the lone pair on your heteroatom. Okay, if you can eliminate small neutral molecules like carbon monoxide, water, ethylene, you'll see that a lot. We'll talk about a rearrangement there. And also rearrangements like hydride shifts and methyl shifts in order to form the more stable carbocation. We'll see a lot of that as well. Alright, so let's take a look. The other thing, before we start talking about the specifics, is that we can look at heteroatoms. Now when you look at isotopes, the carbon-13 isotope is about 1%. So you're going to see a small M+1p. 1%, 1/100th of the intensity of your regular M+ ion. Okay? What about M+2? Oftentimes with M+2, it's 1.1% squared. So you don't really see a lot of that. So just be aware, M+2 should be really small. For bromine, if you look at the isotope ratio, M+2, bromine 81, is almost the same abundance as bromine 79. So if you look at M+2, it'll be unusual because it's almost equal to the size of M+. If you have chlorine, remember, chlorine 35 and chlorine 37. Chlorine 37 is about a third of chlorine 35. So chlorine 35 is 75% natural abundance. Chlorine 37 is 25%. If you look at the M+2, the height, the intensity will be about a third of M+. Iodine only has iodine 127, but what's interesting about that is iodine is so large and heavy that you'll see a gigantic gap between your fragments, between one that has iodine and a fragment that doesn't have iodine. Nitrogen, look at your molar mass, it tends to be an odd number. And if sulfur is present, sulfur 34 is about 4% of the sulfur 32. So you'll still see a small increase in the height of your M+2 ion. Again, here's your isotope abundance. Okay, let's take hydrogen, pretty much 100%. Deuterium and tritium are extremely small. Carbon-13 is about 1%. N15 is about 0.4%, so we really don't see any effects from N15. Usually when we're working with peptides and proteins and we want to do N15 NMR spectroscopy, we have to actually come up with conditions so that it gets incorporated. Oxygen 16, this is almost 100% again. This is only 0.2, so we don't really see anything significant there at N+2. But here for sulfur 32, 4% sulfur 34. So you will see that on your mass spec. Chlorine 35, 75%. Chlorine 37, about 25%. So that's why it's a third of this height. Look at bromine. Bromine 79, about 50%. Bromine 81 is about 50% as well. That's why those two heights are about the same. Okay? Alright, so let's take a look at a mass spec with chlorine. Okay, here's your mass spectrum with chlorine. See this? Here's my molecular ion, 78. But the M+2, look at the height. This is about 1/3 of this one. This is my M+2, That's from chlorine 37. Now, if you look at this one, see how I have that same pattern? So the chlorine is actually still present in here. So if I take this number 78 minus 63, this is the loss of the methyl group. Look at that, the loss of the methyl group. And since the chlorine's still present on my cation, that's why I still see my 1/3 height between these two. So 63, 65, I lost my methyl group here. Now, what about this one? 43. So 43, notice I don't have that M+2 pattern. The reason is I just lost this, and 43 is going to be my propyl cation. Isn't that gorgeous? Oh, it's so pretty. Okay. Mass spectrum with sulfur. So remember we were saying that it was only 4%. So you're not going to be measuring it like we just did with the chlorine. However, see this trend right here? It was M+1 is lower, and then it went up with M+2. Now if it were only carbon, it would be that much lower. It would go down even further. But the mere fact that the M+2 is larger than what you would expect suggests I have sulfur in here. Okay, so this is 76. That's my molecular ion. This one right here at 78, that's going to be my M+2 with the sulfur 34. Okay, now let's take a look at 76 minus 61. Loss of a methyl group. Could be here, probably not, could be there. Then if I have a plus charge here, the lone pair on the sulfur stabilizes that. So, loss of a methyl group gives me here, since the sulfur is still there, notice that it went up right there. Alright? If you look further, here's 45, 6, 7, 8. Let's see if we can figure out the 48. I'm not sure we can. But basically, let's see. If I lose this methyl group, we already said that would be there. If I go further, if I lose an ethyl group, that's going to be 76 minus 29. And I'm not sure that's going to give us what we want. That gives us 47, 45, 46, 47 right here. Okay, so this looks like the 48 and it got obtained a proton. All right, but definitely, look at this pattern right there. That has a sulfur in it. This has a sulfur in it. Okay. Bromine. Oh, look at this bromine. How can you... Look at this. This is just so gorgeous. Look at it. These are almost even in height. Bromine 79, bromine 81. So when you see the molar mass for bromine is like almost 80, 79.9 on the periodic table. There is no such thing as a bromine 80. It's bromine 79, bromine 81, but they're almost equal in natural abundance. Here, look at the 43 right there. I lost a bromine. That's why I don't see that equal peak. And that's why you have this huge gap, because it's such a large molar mass. Okay, what about alkanes? So you're going to be looking at your stable carbocations. Okay, so here, molecular ion, not large, got some branching. Lose my methyl group, I can form a secondary. Can you lose a methyl group here, and then you'll get basically migration, but you're going to get your secondary. Losing 29, you're losing your ethyl group. Okay, if you lose your ethyl group at 29 as a radical, then can you get a primary carbocation? No, you're going to get a shift and get a tertiary. That's why we were already talking about, right? When we were talking about E1 and SN1, we were talking about carbocations and their stability. You're going to get hydride shift, get a tertiary carbocation. 43, okay, so that's going to be cleaving off here. Okay, 43 here, 43 there. Okay, what about resonance stabilized cations? So remember we were saying if you have a double bond, okay, here it is, you get a nice molecular ion. You have a double bond, we actually cleave at the allylic position here. The reason is when you form your allylic cation, you have resonance stabilization. Okay, so that explains your cation of 55, right? And the loss of 29. So you're going to have a series of fragments And if you look at the Silverstein book, you'll see a series of fragments. You just have tables of fragments that are common to lose. Okay? And so you can get an idea of their molar masses. When you have an alcohol, you tend to lose water. So that's why we don't see it. Okay? We tend not to lose just a hydrogen, but we tend to lose water. Okay? So that's why this is losing water right there. Okay? This one, I lost water and a methyl group. Okay? Here's an aromatic. Okay? So this is ethyl benzene. Our molar mass is 106 right there. 106 minus 91. What does that give you? So that loses 15. So I lost a methyl radical to form this. So let's take a look at these guys. So here on the slide that we saw previously, I had a CH2, CH3. I lost the CH3. This is where you would lose, okay, where you have your cleavage. Now why is that? You lose your R group here. Because when you form your tropylium ion, this is what you actually see. But look it rearranges and it forms C7H7, both of them C7H7 plus. But this is an aromatic ion. Because it's aromatic, it's very stable, which is why we see such a strong peak at 91. It can rearrange, losing an ethylene group, because remember we were saying that small neutral molecules like ethylene can be lost easily. Gives you 65, and then you lose it again, gives you 39. So you can take a look at that pattern. Here's 65, here's 39. They're not very large. The biggest peak that you need to be aware of when you know that you have an aromatic is looking at 91 for the tropylium ion. Look at this example though. Okay, this example, I don't have a tropylium. I can't form a tropylium. This is a carbonyl. If I lose this as a radical, then I just have a plus charge here. 77, C6H5. And then from here, if I lose an ethylene, I get 51. So it's a slightly different pattern. If I do a McLafferty rearrangement, these are really, really cute, by the way. I mean, really immensely cute. When you see the mass of your fragment is even, doesn't mean it's always McLafferty, but you're thinking, I might have had a McLafferty. R could be oxygen, like you're looking at an ester, but ketone, aldehyde. What's key is on your alkyl chain. Alpha, beta, gamma. You have to have a gamma hydrogen. Alpha, beta, gamma. This hydrogen moves to this oxygen, moves down to form a double bond here, and this breaks and forms a double bond. If I had a longer chain like an R group here, then I'd have the R group here. So this is your cation that you're going to be seeing on your mass spec as your mass to charge ratio. This, what you'll have lost, is basically an alkene fragment, ethylene or larger, based on the McLafferty. The acylium ion. So going back to losing that carbonyl. So when we have an acylium ion, if we actually, let's say, cleave this, right, then this becomes positively charged acylium ion. Okay? So you can actually see this. That should be a radical. You can actually see this because of resonance between the two. Okay? So you lose your radical, and you see that. Alright, so let's take a look at this one. 2-hexanone. So here's my molar mass. Lost 15, so I lose a methyl group. Okay? If you look at 2-hexanone, and you say, look at, here's 43. So 43, let's draw the structure out. 2-hexanone, 1, 2, 3, 2, 3, 4, 5, 6. Okay? So, methyl group, that'll form the acylium ion. Okay? If I form the acylium ion the other way, Cleave the other side of my carbonyl, that would be the 29. Well, let's see, 28 plus, sorry, not 29, 28 plus 15, that'd be 43 right here. So the cleavage is two places. If you do it, you can cleave on one side of my carbonyl, losing the methyl. You can cleave on the other side of the carbonyl, and then what you'll see is you'll see 43, that's my psyllium ion. If I cleave on the other side, I have a C4, H3, 4, 5, 6, 7, 8, 9. Okay, that would be what, 50, 48 plus 9, 57. So we would see 57. That would be if I cleaved, had my carbonyl as a radical, and I have a carbocation. But what's 58? That's an even number, so let's take a look. We can actually do a McLafferty. If you do a McLafferty, 1, 2, 3, what are you going to lose? Okay, 1, 2, alpha, beta, gamma, you lose propene. So what is propene's molar mass? That's CH2, CH3, that's 36 plus 6, that's going to be 42. So 100 minus 42 gives me 58. So this one, the 58, this is from my McLafferty. The 43, this is CH3C double triple bond O, a psyllium ion. Okay, so let's do some practice problems. All right, when we do practice problems, what we're going to do is with a combination of IR and mass spec, we're going to try to determine basically our molecular structure. Okay, so if you look at this, this is above 3,000. So that's my sp2 carbon-hydrogen stretch. So we're thinking alkenes. Okay, how many? I don't know yet. Let's find out. This one, I have alkyl groups because that's my sp3 carbon-hydrogen stretch. And look at these guys. Oh my gosh, those are your vampire teeth. So that's going to be at 2,700, 2,800. Those are my aldehyde carbon-hydrogen stretch. Okay, so you have an aldehyde. And look at here. This is around what, 1710, 1715? I have a carbonyl. This in combination with these two, you know you have an aldehyde. Okay, now if I look over here at 1500, that's kind of low. I also have a weak one over at 1600. Those are my carbon double bonded carbon stretches. Okay, I'm happy with that. And then this isn't great because here, when they collected their IR spectra, they had to subtract out their solvent. But you're seeing some strong peaks around 700. So you're thinking, let's say you're thinking, why did I put an arrow there? Maybe I'm indicating maybe we have an aromatic. But we know alkenes are here too. So we know we have an alkene or an aromatic. And we definitely have an aldehyde. Okay, so C double bond. C stretches. Okay, we don't see anything broad, so no hydroxide, no nitrile, no triple bond. Okay, no NH functions. All right, let's take a look at the mass spec. Okay, so here at 134, okay, right here, 134 is my molar mass. And I lost one at 133. Well, that's good because I was thinking aldehyde, and that would be very indicative of losing an aldehyde. What about 105? So 105, that means I lost, what, 29? Let's see. 134 minus 105 is 29. So I lost something like, there are two things you could have lost. CHO or C2H5. Since we already know we have an aldehyde function, we probably lost a CHO. Alright? So this is losing my aldehyde. But notice that when I lost my aldehyde, I have something that has a mass of 105 without the aldehyde. So what could that be? If we look here, 80 85, 90, 91. Aromatic. Not only that, we know that the 91 is a tropylium ion. So whatever I cleaved has to have a CH2 and then something else. Okay? Because that CH2 cleavage after the CH2 gave me my tropylium ion right there. Okay, so right now what I have is I know I have an aldehyde. I know I have a CH2, and I know I have a benzene. Okay, so if we calculate the mass there, that's going to be 77, okay, plus my CH2. Okay, so that gives me my 91, and then my 29. That gives me 120. So the difference between 120 and the 134 is 14. So I have an extra CH2 present in my molecule. Okay, so right now we already know that I have an aromatic ring, I have 2 CH2 groups, and an aldehyde. Okay, so most likely 91, I lost 43, so I've lost this much. 29, most likely this, losing my hydrogen. Okay, so we don't have any more oxygens in the molecule. Alright, so what we know then from our mass spec and our IR is we have an aromatic ring, we have an aldehyde, we know we can cleave right there so we can form the tropylium ion. So there are 2 ways we can go. You can form this, or you can form this. Okay? My suspicion is more likely this. Okay, so what are our assignments? This is the first molecule, that's the other side. So the way I've split it up, I've got my fragments here, I have my fragments there. So molecular ion, I lose my hydrogen, okay? Then I lost 29, the CHO. Then I have my tropylium right there. Okay, so that's the CH2 there. All right, and then this one I have a CH3 and it's right off of there. Okay, which is more likely to be stable? This one, because I'm forming my tropylium aromatic. Okay, let's do one more example. Okay, let's do one more example. As you can see here, I have sp2C stretches, sp3C stretches. These are very small. I have a carbonyl stretch, C double bond O stretch. It's at about 1700 or so. So there's some conjugation, not a lot. I see basically around 1600. I see the carbon double bond carbon stretches. Okay. I also see that we have some aromatic stretches. It's a little bit blurred again. Like I say in a previous example, we have to be aware that we had to remove solvent. So from this IR, we know we have carbon double bond carbon, alkyl groups, and a carbonyl. Okay, alkene, conjugated, out of plane. No hydroxyl, no amine or amide, no nitrile, no terminal alkyne. Okay, very few alkyls. Okay, so we see the mass at 120. We see 105, so the loss of a methyl group. We see 77, which means I have something directly attached to my benzene ring. So I'm not getting a CH2 on the benzene ring because I would get the tropylium, just directly 77. And then a 43, which could be either C3H7 or it could be C2H3O. So an acylium ion. Like I say, back here, we saw that it was something has to be directly attached to my benzene ring that can't form a tropylium. Okay, so we don't see no odd numbers, so no nitrogen, no iodine, no bromine, chlorine, or sulfur, because we don't get the M+2 peaks, no large gap. Okay, so you know these guys. All right, so let's take a look at what else we could do. Okay, something that would fit, all right, with our mass spectra and our IR is a ketone. It would cleave here. This would be 43. I would form my carbocation. This would be a radical. Or I can cleave here. This would be a radical, and I would get my 77 carbocation. If I lose my 15, okay, then I'd form this as my psyllium ion. Okay, so 120, my molar mass. 77, cleavage here. 43, cleavage there, and this is my carbocation. Minus 15, cleavage on this side. Okay. What about this IR? Oh, you've got some nice, a lot of stretches here. We've got some alkene CH stretches. We have alkyl CH stretches. We see no carbonyl in there, so we don't have to worry about carbonyl groups. We see around the 1600 a nice carbon-carbon double bond stretch. 700, 750. Might be thinking about aromatic. Maybe there's something else in here. Let's take a look. Look at that. Bromine. Look at that. It's beautiful. M plus and M plus 2. I lose the bromine. That's how I get the 105. So from here to here, I lose a bromine. And then from the 105, so from here down to here, that's 80, 85, 90, 91. So I have a tropylium ion. So I know I have a benzene ring and a CH2. Okay, so these guys, so this is just losing directly, getting the benzene ring is my carbocation, and 51, remember, that's going to be losing my C2H2. Okay, so let's take a look. We have an alkyl stretch, carbon double bond carbon, looks like, I think it's actually 700, 750. Okay, the outer plane CH aromatic bend, but also notice there were some other peaks there. So if we go back, remember, bromine stretches, carbon bromine stretches between 500 and 600 or so. So that's why the fingerprint region is very characteristic, but you want to be careful as you assign those because there's so much overlap. Okay, so we have bromine, we lose it, get the tropylium, okay, C7H7, okay, we have a 14, 105, okay, and then just your phenylcation. So we could be losing, if I lose my bromine, I would get this and a rearrangement, so I get a secondary carbocation. Likewise, if I lose a bromine here, it would be secondary. If I cleave here, I'd form my tropylium ion. Okay, for this one, I'd have to lose both the bromine and the methyl group, so it's, okay. And then from there, I would just basically lose this part, okay, to get my phenyl cation. All right, so these are basically the two possible structures you could probably come up with both this IR and mass spec. And then basically in your attachment on Canvas, you'll be doing exactly the same thing with the structure determination and the assignments on your IR and mass spec peaks.